A freight train rolls slowly, almost languidly, across a sprawling steel bridge, the sun glinting off its countless cars. Each one, a ton of steel and cargo, is pulled by a pair of powerful locomotives at the front. The massive train is roughly 3 kilometers long, heavier than some naval vessels. As the engines work in tandem, the sound of their rhythmic chugging echoes in the surrounding valleys. Yet, as we observe, an interesting sight unfolds. Midway down the train, a distributed power unit springs into action, accompanied by another at the rear, creating a harmony that belies the immense weight they are straining against. Why are these enormous locomotives set up this way? A train this immense, filled with cargo and stretching across miles, is a marvel of engineering. However, it also invites unique challenges. How can a machine this size effectively manage the immense forces and weight it carries? How do engineers prevent mechanical failure under the strain of such heavy loads? Questions of this nature lead us to explore the world of distributed power systems, where locomotives are not merely situated at the front and back, but also strategically placed within the train itself. By the end of this journey, we will uncover the surprising mechanics behind why the largest rail freight locomotives pull from the middle of the train. To understand the purpose of distributing power units throughout the train, we first need to grasp the basic physics of train movement. The fundamental forces at play are tension and compression, which work hand in hand to maintain the stability of the train's structure. When a freight train accelerates, the individual cars experience both buff and draft forces. Buffing occurs when a car pushes on another car in the direction of travel, while drafting occurs when a car pulls on another car. These forces can be immense, especially when the train climbs uphill grades. On steep grades, the pull on the coupler, the mechanism that connects individual cars, can exceed 1 million newtons. This is the breaking point for standard knuckle couplers, which attach the cars together. In other words, if too much tension builds up, the couplers can snap. For reference, a force of 1 million newtons is roughly equivalent to the force needed to lift about 100 tons. To prevent such catastrophes, engineers deploy distributed power units positioned not just at the front but also at various points along the train, including near the middle and at the rear. Imagine a heavy freight train ascending an incline, with its load bringing it to a near halt if too much force builds up. The solution lies in using multiple engines that can spread out the burden and balance the forces across the entire length of the train. As the front locomotive climbs the grade, the distributed power units help to maintain a uniform tension throughout the train by mitigating the shear forces acting on the couplers. This effectively prevents the excessive buff and draft forces that could lead to mechanical failure. To illustrate this, let's consider the Union Pacific's coal trains, some of the heaviest freight operators in America. Typically, these trains can reach lengths of up to 3.2 kilometers and weigh around 20,000 tons. The distributed power system on these trains allows for a more even distribution of pulling power. For example, when a train of this magnitude approaches a gradient of 2%, the extra traction provided by the distributed units can help reduce the stress on the couplers, thus preserving their integrity and avoiding costly breakdowns. Some may think that simply adding more engines could alleviate the strain on the front coupler, and that would be true to an extent. However, relying solely on the front locomotive would result in an extreme tension that could lead to catastrophic failure. The conventional wisdom might suggest that more horsepower at the front can solve the problem. But here lies the charm of engineering. The true solution was to distribute that power throughout the train's length. The innovation lies not solely in increasing power, but in understanding the complexities of load distribution. As we delve deeper into this topic, there is an important aspect to consider: efficiency. Standard locomotives are designed to operate at high power, but they also consume more fuel if pushed too hard too quickly. By transitioning from a singular powerful locomotive to multiple distributed power units, engineers manage to optimize fuel usage. The engines work in a synchronized manner, reducing unnecessary workload on the front units and ensuring maximum efficiency. Now, let us pause for a moment and reflect on a question that may have crossed your mind. Which of these machines would you least want to be standing next to? A 2,000-ton crane? A passenger airplane? Or a freight locomotive pulling countless tons of cargo across the landscape. Our perception of safety shifts dramatically when scaled up. The sheer size and operational mechanics of these machines reveal vulnerabilities we might overlook in smaller contexts. Returning to the subject at hand, one common false belief is that the only way to gain control over massive trains moving heavy loads is to attach all the power directly to the front. A surface-level understanding might suggest that if you need more pulling power, one strong engine can certainly solve the issue. However, spreading the power enables a better grip on the nuances of mechanical stress and the physics of weight distribution. Engineers design these systems to counteract the very dangers of load concentration, which can induce stress on connectors and lead to failures, a stark reminder of how engineering gives due regard to unseen forces at play. So, what is the real trick to this exceptional engineering strategy? It all comes down to creating a balance of forces. By activating units that are distributed across the train, engineers can avoid reliance on one single point for power transmission. This strategy allows for a sophisticated interplay of tension control and reduces the risks associated with heavy hauls on significant grades. In examining the larger implications of distributed power systems, it becomes evident that they represent a clever synthesis of physics and practicality, an example of how modern engineering takes the complexities of load dynamics and transforms them into functional solutions. Lastly, let us take a moment to appreciate the ingenuity wrapped up in the invisible engineering that surrounds our daily lives. As we traverse the landscape of large rail freight systems, we see the marriage of power, precision, and practicalities encapsulated in the design of locomotives. Each decision, from the placement of an engine to the materials used, is founded on the principles of safety and efficiency, guiding us to engineer the heavy machinery that keeps our world connected. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. As we explore further into the mechanics of distributed power systems and freight trains, we can draw parallels from other heavy haul scenarios. Consider the mining industry, where massive haul trucks, such as those used in open-pit mining operations, can carry payloads that exceed 300 tons. These behemoths, like the Caterpillar 797F, are designed to optimize efficiency while managing substantial weights, much like our trains. Operators don't merely rely on the truck's power at one central point, instead, every component is calibrated to distribute stresses evenly across the chassis. This principle also holds true in rail operations. By utilizing a distributed power system in freight trains, mechanical stress can be independently managed, much like the way a mining truck disperses the load across its multiple axles. Standard rail freight cars sit on either 2 or 4 axles depending on their design. However, it's crucial to understand that the load must be spread effectively across these axles to minimize wear from dynamic forces, particularly when traversing rough tracks or grades. Using the example of the BNSF Railway's freight units, they often deploy distributed power systems when moving long coal trains across the rugged terrain of the Powder River Basin. Though each unit weighs around 200 tons with a power output comparable to 4,000 horsepower, the real marvel is in how these units seamlessly communicate with each other, synchronizing brake application and acceleration to mitigate those aforementioned forces. As a result, a train can boast enhanced reliability and efficiency, with reduced likelihood of coupler failure or unexpected breakdowns under pressure. Diving deeper into the realm of physics, we encounter concepts like momentum, inertia, and the potential energy that can build up as a train ascends a hill. When fully loaded, rail cars can accumulate momentum sufficiently to pose risks when approaching a descending grade. This momentum influences how the weight of individual cars interacts within a distributed power arrangement. For example, when a train requires braking, the distributed power systems will adjust power and braking force across the length of the train, effectively converting that built-up kinetic energy into a controlled stoppage. To truly grasp the significance of distributed power, consider a situation that transpired in 1991 involving the Southern Pacific Railroad. During a routine transport of loaded iron ore trains, the company faced a critical failure when excessive tension caused multiple couplers to snap due to buffer and draft forces. This incident revealed vulnerabilities that were born from improperly managed forces within the train. Engineers quickly learned from this failure, thereby leading to the widespread adoption of distributed power units to safeguard against similar catastrophes. Let us take a moment here to delve into the components involved in this ingenious system. Distributed power units rely on advanced technology providing real-time feedback across the train. Each unit is equipped with communication systems that not only transmit data but also receive it, forming a virtual chain that holds the train together electronically. This system operates on wireless technology, allowing each unit to receive commands from the lead locomotive without the need for physical connections. As heavy-haul trains traverse varied terrains with sharp grades, distributed power units offer critical adaptability. This advanced communication allows power adjustments to occur in real time depending on factors such as gradient, weight distribution, and speed. Engineers estimate that incorporating these technological advancements has reduced the risk of mechanical failure due to tension by approximately 30%, a remarkable stat when considering the sheer forces at play. In addition to efficiency and mechanics, the energy requirements of these systems yield fascinating insights into sustainability. With growing environmental concerns, railways are faced with the challenge of reducing their carbon footprint. Distributed power arrangements help achieve this by allowing multiple locomotives to operate collectively, enabling each engine to work fewer hours per shift through effective load management. This reduction translates to lower fuel consumption, which provides both operational and environmental benefits. Extending the conversation of safety and efficiency further, we can draw attention to the maintenance issues associated with long freight trains. Distributed power systems not only ease the physical strain on equipment but also facilitate easier maintenance schedules. Traditional single-location diesel engines require substantial time for upkeep, while distributed systems mean maintenance can be performed on individual units without disrupting the entire operation. This modular approach allows rail companies to maintain readiness and operational integrity, fundamentally reshaping the dynamics of freight logistics. Now, as we start to conclude our examination of this engineering marvel, let us consider a parallel from history, the development of long-distance transportation logistics over the centuries. The introduction of rail networks revolutionized freight transport by eliminating reliance on animal locomotion. Just as trains advanced the capabilities of transport, modern distributed power systems continue this legacy, unveiling new possibilities for transporting heavy cargo swiftly and efficiently. What we once believed was the zenith of transportation engineering has now transformed again, showcasing not only advancements in technology but also a deeper understanding of physics and the dynamics of mechanical systems. The collaboration between engineers who design these power units and the operators who implement them is a testament to the evolution of the industry. As trains stretch across continents, they carry more than mere cargo, they transport innovation. One final thought as we gaze into this remarkable engineering process: consider how this technology influences the global economy. The ability to transport immense quantities of goods swiftly from coast to coast is essential in a globalized world. This mechanism underpinning logistics extends far beyond freight. It shapes supply chains, affects trade policies, and even impacts everyday consumer products that rely on rail for distribution. As the energy-efficient model of distributed power continues to gain traction, we realize its implications are profound and essential for a sustainable future. As we reflect on this exploration of why the largest rail freight locomotives pull from the middle of the train and why distributed power is a cornerstone of modern logistics, the intricate design of these systems emerges not just as practical solutions, but as a celebration of human ingenuity. They remind us of our capacity to harness the laws of physics to innovate and advance our society. The machines that move the modern